Afternoon, everybody.
Good afternoon, Professor.
All right, so just a quick reminder that we have another midterm on November 15. It'll be the same format, same everything, just a different material. So everything from the last midterm until this Friday. So that's what we have. Last time we started talking about how stars die, how after they finish all the hydrogen in their cores, when they turn it into helium, producing energy, they begin to die. So today we're gonna continue to talk about how stars die, which stars that are low mass, stars like the sun, all the way up to 8 times the mass of the sun. What happens through all the last stages and how they die. And then we will begin with how high mass stars are different from low mass stars. And we'll see some similarities and some differences. So here is a summary of the life cycle of a low mass star, which we talked about how it starts as a protostar, then it goes to the main sequence, which is when it's fusing hydrogen into helium in the core. After that's over, then the star gets out of equilibrium, right? During the main sequence, everything is in equilibrium. It's called hydrostatic equilibrium, where gas pressure and gravity balance each other out perfectly so that the star neither grows nor it shrinks. It stays the same and it produces energy in a healthy way. And a star spends about 90% of its life in that stage. When that's over, the core can't fuse anymore because it's all helium. And so it begins to shrink and it gets hotter and shrinking. And then there's a shell around the core that begins to fuse the hydrogen that is still outside of the core. It begins to fuse that hydrogen into helium. That is not a stable way to fuse hydrogen. So we will see today, anytime that a star fuses any element really, but hydrogen outside of the core, things go out of equilibrium. So what happens is that shell that is fusing hydrogen very fast and very hot produces a lot of gas pressure that pushes the envelope of the star, you know, the outer layers, it pushes them dramatically until the star becomes a red giant like the ones I have behind me. So then that's where we ended last time, and we were going to see what happens next. You can see already that there's going to be a little intermission, and then it goes back to being a red giant, and then it's the death of the star. So during this red giant stage, the core continues to shrink. And so my question, just to remind you, what happens to the temperature of the core of a star if the core continues to shrink? What happens to its temperature? If a core continues to shrink, what happens to its temperature? And the options that I'm going to give you are just A, it increases, or B, no, sorry, A, it decreases, or B, it increases. So here it is. What happens to the temperature of a shrinking core? As a core gets smaller and smaller, and remember, it's the same amount of mass, right? It's becoming smaller and smaller because gravity is winning and it's pushing it. So there's no more fusion, so things go out of balance. Gravity wins on the inside and it shrinks the core, and it becomes, well, I'll say it, it becomes denser and denser. But what happens to its temperature? Does it get hotter or does it get cooler? And I'm letting more people vote because I see that there is a disagreement. So Does it get hotter or cooler as you shrink gas? What happens to it as you compress it more? What happens to it, to the temperature? Okay, no more people voting. So the results, that's right, 2/3 of you got it right. So the temperature of the gas increases. The temperature of the core increases, even though there is no more fusion, right? So I can see why some people, 1/3 of the people chose option A, because the core is not fusing anything. It's not replenishing its heat. However, there's another way to heat gas, right? Which is by compressing it. So since gravity is winning here in the core, and the core is shrinking because of that gravity, then it gets hotter and hotter and hotter. So how hot? Well, is it hot enough for helium fusion? And how hot does it need to be in order for helium fusion to occur? And the answer is 100 million degrees Kelvin. So if you remember last lecture and a few lectures ago, we talked about how the temperature of a gas needs to be at least 10 million degrees Kelvin in order for 2 protons to have a high probability of actually running into each other, and for the strong force to take over and bind them together and turn them through a series of steps, turn them from hydrogen into helium. Now, when you have 2 heliums, when you have a helium, it's a lot harder to get it together with another helium. Why? Because each helium has 2 protons, 2 positively charged particles. So 2 positives with 2 positives is a lot more repulsion. So it's a lot harder to get 2 helium nuclei to actually come in contact than to get 2 hydrogens to come in contact. Does that make sense? So the more charged particles you have, the harder it is to get them to come together. So for that reason, hydrogen fusion requires about 10 million Kelvin, but helium fusion requires about 100 million Kelvin. So we're talking about a core that started off at maybe 10 million Kelvin, maybe 15 million Kelvin, in the vicinity of 10 million Kelvin, while it was in the main sequence. But then it turns all the hydrogen into helium, and then it can't burn or fuse helium. Why? Because of this extra repulsion. So it shrinks and the temperature goes up, 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 up as it's shrinking and shrinking. Meanwhile, the rest of the star is like going crazy because there's a shell that has fusion and the rest of the star is growing bigger. So it's a little counterintuitive because you have the outside of the star that is becoming bigger and bigger, while the inside, the core, is becoming smaller and smaller. Finally, it gets hot enough that it reaches this magic number, which is about 100 million degrees Kelvin, and helium fusion can begin. So what kind of fusion do you get when you have helium fusion? So if you remember, fusion was when you get smaller nuclei, you get them together and they form heavier nuclei. So in the case of hydrogen fusion, 2 protons, what's the element that has 2 protons? Well, it's helium. In the case of helium fusion, turns out that fusing 2 heliums doesn't work. And let me show you a periodic table here. So here you have the elements in the periodic table, and the little number in the corner, in the upper left corner, tells you how many protons each of these elements has. So hydrogen over here in the corner only has 1 proton. If you put 2 together, if you have 2 protons, then you get the element with the number 2, which is helium. If you put two heliums together, you would think, okay, so I get what, number 4, which is beryllium. Turns out that beryllium is not a stable element. And so you can't make it just with fusion, right? We don't have time to cover all the reasons why, but it doesn't work. So what needs to happen is actually 3 heliums coming together. And so that you end up with an element that has 3 times 2, 6, right? 6 protons. So what is that? 3, 4, 5, 6. Here it is. So you get 3 heliums, and that gives you a carbon. So carbon fusion, I'm sorry, helium fusion leads to carbon. In the same way that hydrogen fusion released energy, it's the same with helium. When you put 3 heliums together, you get a carbon and energy that is released. So the star goes from having a shrinking, inert helium core to suddenly getting hot enough to be able to fuse. Why is carbon stable? Isn't it a noble gas? Well, it has nothing to do with being noble gas or not. It has to do with how quickly its subparticles decay. So, but carbon is stable. And in fact, most of the elements are, or at least the ones that we're going to talk about, are stable. So very good. So we go to a star that finally has a helium burning core. And by the way, you will see a lot the word burning in the textbook, and sometimes I will say it too. I try to say fusing instead of burning, but sometimes we use the word burning. It's not a good word, because whenever you think of burning, burning is like a chemical reaction, right? Like when you have a flame and you burn something, and that's not what happens in the sun. The sun doesn't have fire, right? I mean, a lot of TV shows and everything say that that stars are balls of fire. They look like fire, but there's no fire. There's no chemical reaction. It's a different type of reaction. It's a physical reaction, right? It's fusion. So forgive me every time that I say burning, I mean fusing, but you will see it on the textbook, burning, fusing. We use both words. Anyways, helium fusing stars get to be stable again because they neither shrink nor grow. As long as you have fusion in the core, you have at least a temporary balance. It is an equilibrium that is not long-lived. It's a very short phase, but for a little while, the star shrinks a little. If you can see here during this phase, it's still bigger than when the sun was in the main sequence. And like I said, it doesn't last very long, because part of the problem is that during this stage, you have a core that is fusing helium into carbon, but it's still surrounded by a shell around it that is still fusing hydrogen. And that shell is going to keep going forever, right? Because that shell, there's an immense amount of hydrogen outside of the core. So it can just keep going. I mean, it'll burn another shell and another shell, and it can burn the entire star. There's not enough time for that because the star dies before that happens, but it could happen, right? So anyways, there's after the red giant, there's a helium burning stage, which is very short. And then eventually all of the helium that was in the core will become carbon. So it's a repeat of what happened before. We had hydrogen turning into helium, then the entire core is helium, and then it shrinks. And then it gets hot enough, and then helium starts burning or fusing, and then it finishes all the helium. All of the helium turns into carbon. And the question is, well, now what? Well, you would think the same thing would happen, right? The core that is made of carbon, inert, meaning it's not fusing, begins to contract because again, gravity is going to win. There's no more fusion in the core. But you still have that shell of hydrogen that is fusing outside in a shell. And then you start to get a helium burning shell because there's helium outside of the core. So now you have hydrogen burning, then helium fusing or burning, and then a core of carbon that is not doing anything. So of course, that means since you don't have fusion in the core, that means the star is again going to be enormous. It's going to expand furiously, and it becomes a red giant again. So the gas pressure expands the outer layers dramatically, and the inert core continues to contract. And it contracts and it heats up and it contracts and heats up. And it's trying really hard to burn the next thing, right? So you would think if you just get it hot enough, maybe you can get 2 of these nuclei, which have 6 protons each. Maybe you can get them to come together. The problem is you need a lot of pressure. You need a lot of gravity in order to get it that hot. And the problem is that you would have to get that core to be above 600 million Kelvin. I mean, remember again, right? The sun or stars like the sun started off with a core that was about 10 million Kelvin. So to get to 600 million, it just doesn't happen. Low mass stars can never compress gas enough to get it to that temperature. A low mass star, 8 solar masses or below that, does not have enough gravity to contract the gas enough to get it above 600 million Kelvin. So I'll repeat it because a low mass star can never have carbon fusion. So remember, a star cannot be in equilibrium if there is no fusion in the core. So since we can't do anything, it doesn't matter what the star tries. If it contracts the core, it just doesn't get hot enough to fuse carbon. So at this point, the star is out of luck because it cannot restore equilibrium no matter what. There can't be fusion in the core anymore. So the star just continues to expand. And it was really giant to begin with, right? It's a red giant, but it continues to expand more and more and more. And now there's nothing to stop it. So this is the point for a star that is less than 8 solar masses. This is the point where gas pressure wins finally, and no way to get it back to being a normal star. So gravity cannot hold the layers, the outer layers of gas and some of the dust that has been produced. I didn't really talk about that, but during carbon burning, well, carbon leads to dust, right? So then you have some dust. And so those outer layers that have gas and dust just continue to expand, and they are expelled not very fast, at tens of kilometers per second or tens of miles per second, compared to other velocities in the universe, other speeds in the universe. It's kind of slow, but they are expelled, and this entire outer layers just go away. Yeah, so I'm getting some questions. Why does it continue to expand? So let me go back just to make sure. So whenever you have fusion in a shell, not in the core, but in a shell, that shell is extremely hot. And the fusion that is going on in the shell has an out of balance gas pressure. So whenever there is fusion in the core, there's an imbalance, in a shell, there is an imbalance, and gas pressure will be stronger, and that's why a red giant grows. The thing is, before, let me go back to here. before, the star became a red giant, and then it was said fusion started in the core, so that restored equilibrium for a little while. But then when that equilibrium is broken again, then the star expands and expands, and it continues to expand. Let me get back to where we were. More questions. So why? So why is it then when there is fusion in the core, gravity can hold the outer layers? The reason is the gravity is the same, right? Well, no, actually it's not. It's a little complicated, but gravity, the reason why gravity can hold the outer layers when there's fusion in the core is because the gas pressure that is coming out, that is resulting from the fusion in the core, can be balanced by the gravity. But when you have fusion in a shell, the fusion rate is much higher because it's much hotter than it ever was in the core. So the gas pressure is much greater, and that's why it pushes harder, and gas pressure in this case wins over gravity. What value does it mean when it says tens of kilometers per second? Like 10, 20, 30, 40, I mean, it depends on the star. So I'm talking about 30 kilometers per second as opposed to 300 kilometers per second, right? It's an approximation. All right, so as the debris moves away, the core, that core that was made of carbon that cannot fuse anymore, will become visible. It's like for the first time, you're able to see what's inside a star. And so that hot carbon core that becomes visible is very bright because it's very hot at this point. This is what we call a white dwarf, and next class we'll talk more about those, so we'll come back to this. But this hot core, called a white dwarf, it is so hot that it emits UV light, right? Ultraviolet light. So if you remember, blue light is very high energy, ultraviolet is even higher energy, shorter wavelength. So this ultraviolet light kind of lights up the entire nebula around it, the outer layers of the star that are expanding. And so it begins to glow. And it forms what we know as a planetary nebula. Now, planetary nebula is a bad name because when you hear the word planetary, you think of planets. And unfortunately, they named these things planetary nebula a long time ago when they didn't know what they were, because they were round. So they thought they were kind of like planets, but kind of like a nebula, like a cloud. But it has nothing to do with planets. It's exactly the opposite, right? I mean, it's not the beginning of a star, it's the end of the life of a star. And it looks something like this. This would be like in very high speed, you know, playing it at very high speed, how the outer layers of the planetary or the star, the outer layers of the star continue to expand and expand and expand. They get illuminated by the central core, which you see here as this white region. And because they're made of different elements, they give out light of different colors, just like more or less like when we talked about the aurora in our planet. And then that little core in the center is the white dwarf that eventually it gets dimmer and dimmer as it cools off. So here's an example of a planetary nebula, which is called the Ring Nebula. And in a lot of them, you can see that they're round, and you can see a tiny little core in the center, which is a white dwarf. And you can see just how beautiful they are. These are some of the most beautiful objects in in the galaxy, I think. Yeah, good question. So is it spherical or is it hollow? It is spherical. The reason the reason you see it as being as a ring is because, how do I explain this? So the different layers are piled up on top of each other, so it is thicker, as opposed, like if you have a balloon and you blow a balloon and then you see the edges are going to look darker because you're seeing through more material on the edges than, I'm talking about a more transparent balloon than if you look straight through it. I don't know if that makes sense. I'll try to bring an illustration next time so that I can explain that better. And I'm getting some questions about, is this an explosion of a supernova? No, supernovae happen with high mass stars, and that's going to be next class. So this is the, somewhat peaceful death of low mass stars because there's no explosion. There just comes a point where all the outer layers continue to grow and continue to expand and expand and expand, and there's nothing that explodes. Another question was, does this point here become a black hole? And the answer is no. That corresponds to high mass stars, and we'll talk about it next time. How big is a white dwarf in comparison to planets? It's about the size of Earth, and we will talk about it next time. So it compresses a lot because to begin with, it was a lot bigger, the core, but then eventually it becomes smaller. Let me see, did I get to all your questions? Yeah, I think I did. So I have a few pictures of planetary nebulae because they are quite pretty. And here's, this one is called the Cat's Eye Nebula. This is a picture from the Hubble Space Telescope. And you can see a very intricate pattern, and you can see how there's kind of like shells. This happens because at the very end of the life of a low mass star, it begins to pulsate. It gets really out of equilibrium, out of control, and it begins to expand and contract and expand and contract. And it's actually a very violent thing toward the end. And so every time that it expands and contracts, it creates a shell like the ones that you see here. And it's some of the patterns that you see here has to do also with whether it was rotating and magnetic fields and all kinds of things that make it into a very complicated pattern. Here's NGC 2392. This one, they call it the Little Ghost Nebula, so happy belated Halloween. And here's the Dumbbell Nebula. So there's many, many of them. You can Google planetary nebula and you'll see they're all quite beautiful. A low mass star is defined as a star that is less than 8 solar masses. That's right. Okay, just one more, Spirograph Nebula. All right, so answering another question here, planetary nebulae fade within 1 million years. So again, compared to the lifetime of a low mass star, about 10 million years or so, 10 billion years. Planetary nebula is, a blink of an eye, just about 1 million years or so. Why does it fade? Well, because the gas continues to spread. It's going away from the core, the cooling star. So two things happen. The star is getting cooler because it's not fusing anything. It's not producing heat. And sorry, by star, I mean the dwarf, the white dwarf, the core that is not a star anymore. So it is becoming cooler and cooler. So if you remember, hotter objects emit more light, cooler objects emit less light. So as it's cooling down, it also becomes dimmer and dimmer. And also the shell or the many shells are spreading far away from the star. So, and it is the, I keep saying star, I'm so sorry, from the white dwarf. It is the white dwarf, that core, that is illuminating the rest of the nebula. So if you move it away from the white dwarf, it's going to look fainter and fainter, or less bright and less bright. Eventually, the entire nebula will mix again with the gas from the interstellar medium. And later, if in case you were already wondering, later this interstellar medium that came from the nebulae is going to become, hopefully, another molecular cloud, and then hopefully you will get new stars that are born from the leftovers of these stars. Now, this gas is going to be enriched because the star formed new elements, right? The star during its life formed some more helium, and it formed some carbon, and also a few other byproducts that we don't really have time to talk about. But the bottom line is that the stars that form from the new gas will have more heavy elements than the previous generation. And this means that with every generation of stars, it's going to become easier and easier to form planets, right? Because for planets, you need the solid stuff. You need rocks. You need metals. You need these heavy things. So as stars go through their life cycles again and again, they create more and more stuff that can later be used to form planets and to form humans and to form all the things that we are familiar with. All right. Great. So I have some great questions, and I think I have time to answer them. So does that mean that eventually the universe will run out of hydrogen to fuse? In principle, yes, because a lot of the, okay. Yes and no. So in order for hydrogen to fuse, it has to be in stars. And one thing that I don't really cover in this class is that there is a lot of hydrogen in stars, but there's also a lot of hydrogen in the universe outside of stars. So all the hydrogen that eventually makes it into stars, yes, it will become helium. But there may be hydrogen that is left over that never becomes a star. So great question. Can planetary nebula affect other solar systems due to the disperse of these gases and energy? As you know, there is a lot of space in between stars. So for example, when our sun becomes a planetary nebula, eventually some of the gas from our sun will get to other stars, but it'll be very little. It'll be very thin by the time it spreads out so much. It's a little different with supernovae, but we'll talk about that next time. Yes, so can I go back to, I think, let me see, can I go back to that one? All right. While I answered the last question, and then I'll move on. Okay, can I explain again why a star cannot be in equilibrium if there is no fusion in its core? To really understand, I mean, it's a great question because let me put it this way. I teach another class that is a graduate level class, and it's graduate level, right? Which means you have a lot of physics as background. And then we spend, I believe, about 2 weeks deriving all the equations and explaining why, when fusion does not happen in the core, the star goes out of equilibrium. So the problem with this class is that I try to make it intuitive. right? Because we don't do any of the math, and we don't, like, you guys don't have the physics background. And so the problem is that sometimes this goes a little beyond intuition. But I'm going to try. I'm going to try. When a star is on the main sequence, it has fusion in its core. And the star doesn't have a pretty, the size that the star ends up with is the size where gravity is able to match the gas pressure that is coming from the fusion in the core. I said a lot of words, and I don't know if you guys are following me. But a star on the main sequence can be balanced. The problem is there's only so much gas pressure that gravity from a low mass star is going to be able to balance, right? If you could put an indefinite amount of gas pressure into a star, there's only so much gravity, right? And so if you put a lot of gas pressure in the star, then it'll just expand and it'll win over gravity. So I think that is a little easier to understand. Now, why is it that when there is fusion outside of the core, why is it that that's when gas pressure wins? I think you will have to take my word for this, but fusion in shells will, whenever it happens at a really, really, really hot temperature, and a really fast and furious pace, much more than you ever get in the core of a star. So whenever you have this fusion in the shells, you will get a winning gas pressure that wins over gravity. I hope I didn't get you guys more confused. And I encourage you to read the textbook. The textbook will explain it in a different way from what I explained it. And also ask your TAs, they will explain it in a different way. And hopefully it'll make sense. You might ask, well, why is it that when helium starts fusing in the core, why is it that the equilibrium is restored for a little while? When there's fusion in the core, that makes the core expand a little. And so then the shells are not as hot because they move up. And so then there's less gas pressure than when the core is shrinking. So that's my best that I can try. I'm obviously not going to ask you very detailed things about this in the exam, because again, you would have to be a graduate student taking a long class in order to work out all the physics of why that is. But at the same time, I don't want to just present it as, you have to take my word for this, right? Because no, that's not what science is. Science is trying to figure it out and putting the puzzle together and testing and trying. So I do want you to understand why it is, or at least have an idea of why stars become so big during the end of their lives. Okay, let me get back to this. Oh, I tired myself. Okay, we have 10 minutes left. All right, so.
When the fuel is gone.
Okay, so here's our solar system during the planetary nebula phase.
The sun's core ultimately contracts as it transforms from a red giant to a white dwarf. The expanding outer layers of the sun, called a planetary nebula, drift into space as ghostly shrouds of glowing gas. The planets that survive this process, the outer ones like Saturn and Neptune, are utterly changed by it. the planetary nebula blows away their gassy atmospheres, leaving small, rocky and metallic cores behind. The distant planets, no longer held by the less massive sun's gravity, drift into the vastness of space. Travel billions of years after that, and all remaining heat from the sun has radiated out, and its small, dark surface is the same frigid temperature as the rest of space. The sun is now a black dwarf. Now, billions of years later, propelled by a mysterious and only recently discovered dark.
All right, so I used to say that planetary nebula was the peaceful death of a star. It's not exactly peaceful, right? Because it will destroy our solar system, our planets. And so it's somewhat peaceful. It's peaceful in that it doesn't explode, but it is still violent. It is still not good. Again, this will not happen for another at least 5 billion years, more like 7 billion years. So in about 7 billion years, all of these things will happen. And I'm more than sure then that if humans are still around, they will be somewhere else, not here. Do the planets maintain their orbit during this? No, and I think the video said so, because the mass of the sun is going away from it, and we're left with only the mass of the core. So that will change the attraction between the planets and the core, and so the orbits will change. So here's the summary of the life and death of a low mass star such as the sun. A low mass star, again, defined as less than 8 solar masses. So it begins its life as a baby star, a protostar that came from a molecular cloud. Then it goes into the healthy life, the healthy stage, which is when the star is fusing hydrogen into helium only in the core, not in shells, not in anything else. The star is in this really nice hydrostatic equilibrium, and it spends 90% of its lifetime during this stage. When all of the hydrogen turns into helium, the star begins a series of steps that turn it into a red giant. And from then on, there is fusion in shells around the core, which leads to non-equilibrium, right? To the star is out of equilibrium. So it becomes a red giant. It fuses helium for a little while, but then it becomes a red giant again. And finally, there's no more to fuse in the core because it becomes all carbon and it cannot fuse carbon. And so the outer layers are blown away, becomes a planetary nebula. Eventually, all that is left is a white dwarf. And as the video mentioned, the white dwarf will get dimmer and dimmer until it becomes what is called a black dwarf. So that's it for a low mass star. That's the not so violent. And we move on to what is the most violent, one of the most violent things that happen in the universe, actually, which is, and I'll give you the punchline already, it is a supernova. And this is at the very end of a high mass star. That's what happens to them. And it is a cataclysmic explosion. And that's incredibly powerful. It's one of the brightest, strongest, most energetic things that happen in the universe. And so we're going to go through the steps and how this happens between today and next class. So in the last 5 minutes, I'll tell you about the first stages, and then next class we'll talk about the supernova. So the early stages of the life of a high mass star. So here, high mass means more than 8 solar masses. The early stages are very similar. They're just bigger, faster, brighter, hotter, right? So during the main sequence, hydrogen fuses to helium in the core. And so same thing as with low mass stars, just faster, brighter, hotter. Same thing happens, hydrogen runs out, then there's a core of helium, and then there's a shell of hydrogen that fuses around the core, and the star becomes not a giant, but a red supergiant. So again, everything is just bigger, right? Everything is just hotter. And then there is a brief period of time when helium can burn or fuse in the core. So helium fuses to carbon in the core. So very similar to low mass stars, just bigger. The difference, here's where they diverge. A low mass star, once all the helium becomes carbon, that's it. For a high mass star, it can keep going because it has a lot more gravity, it has a lot more mass. So the core can continue to contract and contract so that the temperatures needed for carbon to fuse, the 600 million Kelvin, can actually be reached. The core can continue to get hotter and hotter each time that it contracts to allow fusion of heavier and heavier elements. So it actually doesn't stop with carbon, it keeps going. And so you get fusion in the core, and then later on in the shells, you get, so there's hydrogen and helium, but then there's carbon fusion, and then there's neon fusion, oxygen fusion, and finally there's silicon fusion. So it can keep going and going and going, and it's the same cycle, right? It grows as a red supergiant, then it's the core shrinks, it gets hot enough to do the next cycle of fusion, and then it fuses, things get a little imbalance for a little while, and then it runs out of that element and it has to shrink again, go to the next element, and so on. One thing to get out of this is that the basic elements for life, which are carbon, nitrogen, oxygen, hydrogen, all of the, not hydrogen, but the heavier ones, carbon, nitrogen, oxygen, they're all made in stars. And maybe you've heard people say things like, we're all stardust, we're all made of stars, and that's what they mean. The universe at the beginning only had hydrogen, and now it has all these different elements that you and I are made of. And so that we were cooked in stars, right? All the elements that went into our bodies were once created or formed in stars. So if you were to see a supergiant after a few of the fusion cycles, this is more or less what you would be able to see. A red supergiant is about the size of the Jupiter's orbit. And the very core, you would see that it's at the very end, silicon fuses into iron. And so you would see a core of iron surrounded by a lot of shells. You would get silicon fusing, oxygen, neon, carbon, helium, hydrogen, all of this. I do not ask you to memorize the order of these cycles simply because it's a lot more complicated than this picture. And again, if you were to take my graduate class, we would go into gory detail about all this, and you would see how complicated it is. But I do want you to remember that the last thing that can fuse is silicon. Silicon fuses into iron, and iron cannot fuse. So let me go into that. This is our last slide. I'll start with this slide next time because it's already 4:50. So yeah, I'll start with this. I'll stop here and I'll stay behind for questions. So by the way, today is the last lecture that is so complicated. From here on, it'll get easier. So have a good rest of the day, and I'll see you guys on Friday. And again, I'll stay for questions.